get started. Okay, thanks everyone for coming, both the ones for in person and also online. It is my great pleasure to introduce Professor Giuseppe Loianno. Giuseppe is associate professor at UC Berkeley ECS department. And prior to joining Berkeley, actually, Giuseppe joined Berkeley in this year, July. And prior to that, he was associate professor at New York University. And prior to NYU, he was research scientist and team leader at Brass Lab of University of Pennsylvania in Philadelphia. And he has received numerous awards. If I read the whole list, it would take like 5 minutes. So I'll mention a few important ones that include the NASA Career Award, DARPA Young Faculty Award, and also numerous awards of best papers in conferences. And he is a leading expert in the field of robotics and AI. So it is great to hear from you, and the floor is yours.
So thank you very much, Nancy, for the introduction. It's really a pleasure to be here and join this new community in California. So today I'm going to present a little bit of work that we've been doing in the past couple of years, especially on how we make robots more agile, adaptive, and how we also scale the number of robots and also the types of environment where these robots need to operate. Let me start just showing you a little bit the progress of autonomy over the last, let's say, 15 years. If you think around 2010, most of people were working in planning and control problems. So everything was working in an indoor environment. You had the familiarity with the motion capture systems, where basically people were using it for indoor localizations. And similar aspects, were starting in autonomous car. They were starting to use sensors to. These are some videos of the DARPA challenge at that time. Then we went to another phase, which is the one of what I call intelligent autonomy, where really people work on the autonomous algorithm and they bring this concept forward in a real world deployment, including the amazing work of Skydio that has been producing very nice results in autonomous drones and also Waymo in autonomous driving. And then we have what I call human level performance, which is where the future is going. How do we make these machines at the same level of humans or even more in terms of intelligence? So these are two cases where humans are extremely good if you think that drone racing or car racing. And these are just two examples on how this is evolving, and we have AI systems that are trying to solve these concepts. However, to get human level performance, we're still very far. If you think what's happening, in all this situation is that there are lots of failure. Failure that comes from, hardware that's not working, algorithm that's experiencing, effects that were out of distribution, basically, effects. You have also very harsh environment condition of operations. If you think, they've done these DARPA programs, Terrain Challenge, where robots really struggle to operate in this underground environment. But you also notice that as soon as we put multiple of these autonomous machines together, the system fails. It fails because it basically lacks the scalability, and you have seen many problems, both in self-driving cars, but also in autonomous racing, where as soon as they immediately notice what was working with one car, you put 3 or 4 cars on the track, it's not working anymore. So really, what I think is the main directions for future research in this autonomy area, I think it's 3 challenges or axes of complexity. One is, how do we make our system more adaptable and safer? How do we increase the efficiency, which for me, means power, time constraint, but also agility, which comes from my side, on how we even shrink the large sensor payload that we have on these robots, and maybe we use just cameras. And then how we scale this to multi-robot systems, but not only in terms of how many robots can I deal with, but also how many types of environment I can deal with, right? So many of the research has been focusing on each one of these axes. People try to make algorithms that are more adaptable and safe. or that are more efficient. But really the challenge is how do you maximize all these three axes and you make algorithms that are, you try to improve all these three aspects. So if we go back to how autonomy is conceived, I don't know if many of you probably are familiar. I think there are, you can categorize all the works in two main areas. One is the conventional autonomy, and the other one is the end-to-end sensory motor policy. So in the conventional autonomy, basically you have generally 4 blocks. That's what people have been using mostly in the autonomous driving cars, also in Waymo. So you have localization, mapping, planning, and control. On the other hand, you have a sensory motor policy where people, try to train a neural network that's getting the sensor input, might be a camera, might be a LiDAR, and then it outputs just the control command to your robots, right? So which one is the best, and why do we need to use one or the other? Well, I don't think there is really an answer. If you look at what's happening, each architecture has some given strength and limitation. So on one side, for example, this one enables collaborative design. It's modular. Your students work, you have multiple students. One student work on planning, one student work on control. Then you come together, you merge all the approach and everything it's supposed to work, right? So it's allow, collaborations within the with multiple people. However, it's very sensitive to uncertainty. You have high-level perception to latency, because you have 4 blocks that they need to parse all the information before you make decisions, and then you have multi-level abstraction synthesis, which I think is the major problem also of this approach. If you think about how localization is solved and how mapping is done and how planning is working, basically they all use like the same perception information, basically image or LiDAR, except that what they do is that they cast that information at a different level of abstraction. For example, the localization may use feature points, but those feature points are not good for planning, right? Because you want a more coarse representation of the environment. So what people do is they generally use, for example, Octomap or ESDF to basically make sure that you identify obstacles in the environment. On the other hand, low domain expertise, low perception to control latency, but the big problem is that this is really not in many cases interpretable. And the other thing is that there is a big data gap. So in many of these robotics tasks, we literally do not have the data. And so what's happening is that you use the data, it's very task specific, and then it's basically not generalizing to a wide range of conditions. But both of them have the big problem that they are difficult to scale to multi-robot systems. So what's the approach that we took? Well, the general idea that we took here is that can we leverage the strength of both solutions? And so can we basically do something that we get an observation? We use these AI machine learning models to abstract some models and representation that are very useful, that could be potentially used by provable or optimal control techniques to guarantee other aspects, in terms of safety and generalizations. And so really the key is that how you choose these models and representation is very important, because we have looked especially at models and representation that can guarantee efficiency and safety. And how do they scale to they can also scale to multi-agent systems. So potentially you have these models and representation that they are compressed enough that if you have a team of robots, you can leverage potential communication between the agents to share this kind of information. And then have either a distributed model or have some kind of distributed representation that you can use to make informed decisions. So let me tell you a little bit what we've been doing, in this area. So pretty much, for example, we are working on problem on how do we make our system more adaptive and reactive with respect to the environment. So we really worked on learning, the dynamics of the system. So what are the dynamics? Basically, dynamics is, can you basically learn these functions that's mapping, state and control at time t to the next state or to the next couple of states in the future. And why this is important? Because this is currently used, for planning and control, and so to forecast your type of motions. Many people, are doing, strong assumptions, like, for example, then the dynamics are constant and known, but this is really not the case in real world scenario. If you think that robots that are picking up payloads and then delivering it, or even if you fly fast, your model doesn't match anymore the reality, because all the aerodynamics effects and all the forces that are acting on your platforms are not the one of your nominal physical equations, right? So the idea that we had here, looking at the state of the art, that's they're trying to solve this gap, but some approach were too slow, they were data angry, or were not adapting really with unseen conditions. So the idea that we propose here is twofold. So the first one is that let's make our model a model that is a combination of physics knowledge and data knowledge, basically. So it's so what we do is that we use two losses to train our model. One is the classic mean square error loss that's obtained from the data that the robot is experiencing in the real world, and the other is a physics-inspired loss, which is obtained from the data of the nominal model. So combining these two aspects, we have shown that you can really generalize and adapt to different types of conditions. The other thing that we have shown is that once you have this model that you can learn through data, you can run an optimization on top of it, for example, model predictive control and so on, that leverage the power of this model. But what you can do is even more. Since you are forecasting future state and future control input through this model predictive control, you can basically leverage some of them to, let's say, compute an error between whatever you predict in the future and whatever your system is giving you in the real world scenarios. And based on this error, you further adapt your network weights in real time. So you can basically adapt your system to unseen conditions and so on, right? So that's the idea. And you can even do more in principle. If you have the uncertainty on this model, you can actually add preferential direction of forecastings that may keep your system exploring some area of where uncertainty is lower or where uncertainty is higher, depending on what kind of stability you want to guarantee on this system. Keep in mind that this system needs to operate at very fast time scale, because you need to update the model at faster time scale than making the decision, because otherwise it becomes basically practically unstable, right? So that's the idea. And so we have shown a lot of things here. For example, we train our model on a simple quadrotor with 4 propellers, and then we say, okay, let's put a payload over it, and let's see if this network is able to adapt in real time, right? So the idea is that here you can see that, for example, it's learning that there is a load, and so it's able to reduce the error on the Z compared to the static dynamics or classic adaptive control techniques. Another idea we had is say, okay, let's put 4 different propellers on the robot, and let's see if this is capable of adapting to these unseen conditions. And you can see that it's doing a much better job than the static model and also the adaptive one, right? So we also tried with wind and so on. So pretty much this is able to reduce to learn new ideas and to learn what's changing in the environment and adapting to it. So the other thing is that we need to. This was done in yes.
Yeah, sorry. I'm just curious about the mathematical structure behind this. So if you go back 2
Yes.
slides. Yeah.
This one.
So these neural dynamics is
Yes.
So if the dynamics are x I equals f of x comma u, it's literally the f function.
It's literally the f function, yes.
And
So that's a neural network. That's basically that's mimicking the f functions.
Got it. So then offline you're learning the parameters of that f function.
Yes.
And then is it the same parameters or different parameters or a subset of the parameters that you're learning online?
Yeah, so what do we do online is that we update the weights. We update the parameters based on what the robot is experiencing on board, but it has a strong prior on what it has learned before, we're just adapting those weights online based on the experience. What's missing is that is the disturbance or is it something that I'm carrying that I'm not able to identify that yet. So it would react the same way to if it's part of the system or if it's an external disturbance.
So when you say that the dynamics or the structure can change in the middle of operation, it's not like you're adding state equations or anything
No.
like that. It's just
I'm just updating the weights of the neural network in real time.
okay. Thank you.
Well,
Makes sense.
so then we need to bring this system to the real world, right? So the idea is that, for that we'll need some mapping, planning, and localization according to the old structures that you have seen. So that, the robot may find a free space and plan through it, right? The problem is that, this is very slow and it's lots of heavy computation and also memory, storage. And the goal is that can we ensure safe navigation without mapping and global planning? Can we have a purely reactive approach that based on what the robot is observing locally, it's able to navigate, let's say, in the environment? So we reduce this kind of block. So the idea is really to go from this kind of architecture, which is really not meant to be agile, because as soon as you have an error, this propagates everywhere. For example, you have an error in localization, this propagates on the mapping and so on, to a type of architecture where we try to merge, we do a first step, merging planning and control, such to improve the agility of our system. So if we look at that, why do we want to do that? I mean, we want to do that also because, the world is changing. So we want to even be able to, deal with the rapidly changing environment, different obstacle configuration, and so on. So we want to be generic, something that, many of the current approach are not able to deal. And these are some of the existing approach which make lots of assumption. Or for example, in this case, they use the LiDAR, which is very task, specific, and its perception is much easier if you have a LiDAR compared to a camera. So our goal is really to reduce also the sensor payload to have only a camera, and are we able to get similar performance, compared to a LiDAR. The other thing we want to take care is that, we don't want to make any assumption on the environment. So we want to generalize to different types of environments. So the first step that we did in this case is, okay, let me grab these. So there are these very powerful visual foundation models that are able to give you, depth of the environment. So depth, imagine that you have this image, it's telling you how far the obstacles basically are. The only problem is that depth is very precise, but it's unscaled. What does that mean? That you don't know how far the obstacle is. It's the same, pretty much kept. The same scale is kept for all the element in the environment, right? However, most of the current stereo cameras, like RGB cameras, Intel RealSense, for example, have the ability to give you a sensor depth directly on chip. This is scaled, but it's very poor. So if you look at it, there are lots of holes that basically makes this depth not usable for the scope that you want to do autonomous navigation in the environment. So here the idea was, first of all, let's combine the benefit of these two approaches. I'm going to use basically the relative depth, and I'm going to correct the scale with the sense depth in the of the other cap, right? So here I make a quadratic optimization problem where I try to reduce, basically, I try to find these factors to match basically the relative depth to the current scale of the sensor depth, right? So that's the overall idea. And you see that the completed depth is very precise. So this was amazing because we tried on some building that were basically uniform in terms of color, and the sense depth was struggling. This model was giving us extremely good results. And you can see in some of these videos how this works. So you can see that this is the original depth, which is all full of holes and imprecise. This is the completed depth, and you can see that's doing a very good job just to do a visual, just based on visual information, right? So that's, you can see the trees, you can see all the structure of the environment, and you don't make any assumption on the specific structure or on the specific, semantics that your environment is showing. So once we have this step, how do we use it for navigation in our case to reduce the mapping? So we don't want to do any mapping. So what does that mean? That we go back a little bit in time to let's use this step and let's try to find the minimum time to collisions for each one of these boxes, right? So each one of these boxes gives the robot minimum time to collisions to the objects that are identified inside. And so basically, pretty much this is projected on the view of the robot, and it's giving the robot the idea which points are most dangerous, or they're gonna be like, most critical in terms of navigations. And the idea is that, once we do some filtering, we keep the most relevant. That's what we care about. And then rather than mapping, we don't care about mapping. We basically get these points, which are purely points in a depth image, and we decide to use, the model predictive control that we used before. But the nice thing is that we embed this constraint directly in the model predictive control here as basically control barrier factor. So these points that are coming from the perception of the environment, they don't need to be mapped in the environment and make the map and so on. What you do is that you directly inject them into your into your control, basically directly, giving some control barrier function, and you choose the parameters, to regulate the motion close to the obstacles and so on. But the idea is that, in this case, you basically navigate without building an explicit map of the environment. Everything is local. What, based on the robot is observing, is just purely reacting. Should I go right, left? But there is not a planner that's deciding that. The model predictive control is doing the job directly from the perception to making a decision for the motor speeds of your robot, right? So that's the overall idea. So we can show that we can navigate. This is what the robot sees, and this is, on top, down, left, down left, you see the reference, and so what we give is a point in space. Go on the other side of the room, and then it's trying to simply react to what it sees in the environment, right? So that's the overall idea. Different light conditions, so you can see that, we made different paths, different light condition, very robust systems, goes to the other side of the room and basically completes the task. And these are some of the results we have. You're going to see that, this is the barrier value of the most of the most critical point, I would say. So we are always in the safety part. So this guarantee is also safety. Based on that representation, we don't have any accumulation of error because everything is relative in terms of mapping. And it's just based on the current view that what the robot is basically seeing, right? So that's the idea. Then we try also outdoor. This is dodging a pole in outdoor environment. And then we also show what's happening, in this case where we go really close to a tree, but we see that we're able to basically avoid it just in that type of environment, right? So great. So we reduce the first block, that's control and planning. So we have a strategy that's preserving safety, improving agility. So now the question is, what's the problem? The problem is that we're still relying on some kind of localization system, which in our case was GPS or visual odometry. So can we get rid of these global localization systems? And why? Because once you have inaccurate localization, basically you have classic drift, and this will bring you to catastrophic crashes. This is generally, for who is not familiar, obtained through generally camera, GPS, VIO, and so on. So really the goal is, can we basically reduce the localization, and we just rely on what's observable locally at that specific time, right? So this will give, improvement in terms of, GPS denied conditions, VIO drift, and other types of conditions. So if we want to visualize this graphically, we want to go from an architecture which has perception with safety constraint and localization to another type of architecture where, in our opinion, you just detect object of interest in the environment, and then you navigate with respect to this kind of objects that are available in the environment. This object can be picked through a dictionary, whatever you like, but it's all relative to what the robot is observing, and it's not subject to a global localization system, right? So what we propose here is sort of what we call instantaneous relative localization. So we'll have two modes. Once we see an object, we basically just track that specific object that's of our interest, which can come, from visual language model or like whatever you would like, even a user prompt. And in the other case, we perform loitering. When we have no object, we should just choose a preferential direction to search. And then once we get something of interest, we continue our navigation. So we're going to have the same, pipeline with still model predictive control and so on, but we'll have two cases. One is the loitering case, and one is the tracking case. But the cost function in our controller, it's basically the same. And the other thing is that we're just switching what kind of environmental cues we are interested in this type of setting. So the architecture, again, is still the same. The only thing that's going to change is that these blocks, which is the object block, will just run when the object is available. When the object is not available, you just basically do dead reckoning based on optical flow, right? And so the idea is here that this is what we have seen before. These are the collision points that we had before. This is our model predictive control that's receiving the collision points. And this is, the estimation that's based on if I see the object or I don't see the object, right? And the same framework as before. So we don't map anything. Everything is based on the current view of the robot, right? So you can see that we can do some kind of missions. This is loitering, purely searching for object of interest in the environment. Then we can switch more and from loitering. For example, in this case, it goes to the task was identified a car in the environment, so it finds the car, and basically it's just locking onto the specific car that it has seen. This was dynamic tracking. For example, it's moving, and we see also that there are some kind of distractors in the environment. Same like element that's like here, but it's still tracking the right person on top of the track. And this one, it's when we show the obstacle avoidance. So we on purpose send the robot higher to see if it was able to track and avoid obstacles. So you can see that it goes down the fence just to avoid the obstacle while still tracking the mannequin that's on the agent. We did even more. So we tried, for example, this is a sort of forest trail to track this kind of car. I think it was 30, 40 kilometers an hour. And this is basically what's happening. This was the car of the DARPA Racer program. I don't know if you're familiar. We got up to 80 kilometers an hour just tracking with our drone this kind of system in this kind of environment. So that was kind of exciting, I would say. So that's the idea. Then this is another track just to see that we can generalize to different type of cars. It's not related to only one type. I think this is the cool view where actually our collaborator put another drones on top just to film what we're doing. And so this is the drone that's basically tracking completely, with what I've shown you, model predictive control plus vision-based obstacle avoidance. These cars at these speeds with lots of dust and so on. So this is another example where we do loitering. For example, this is in the forest. You see the collision points that are the most dangerous that the robot is trying to avoid in real time. So you can see that's basically dodging all the trees and so on in the environment. And then in addition to that, we had the case of this traversing a forest, just purely loitering and avoiding what you find in front of you, right? So that's That's the idea. And then here it's where we show the transition from loitering to tracking, for example. So that's the idea. And similar in the forest, I just skip the first part, which is basically the same. So we traverse everything, and then we find, this can be used really for search and rescue operations. You traverse everything, and then you find, for example, the human on the other side, and you lock onto the target once it's given, once you found. Okay. So in addition to that, so what we did is that what we really propose, it's a model predictive control approach that doesn't rely on any global information, purely local, no mapping. So we really reduce the pipeline from sensing to decision making, because this is a much lighter weight approach compared to all the 4 blocks that were provided, before. However, this can still be kind of cumbersome if you want to implement this kind of approach on really tiny devices. So, especially if you want to control, PWM directly and so on this small kind of chip, right? So the idea is, can we approximate that kind of MPC with a more neural network policy? And that's also something, we've been working on. So how do we optimize this kind of technique, optimal control technique? So in this case, we propose a classic, actor critic approach that's running on the chip. But really what we try to solve is, how can we reduce the training time of this reinforcement learning solution, and how can we cope with the sim to real transfer? So what we do here is that novelty are a curriculum learning approach. But the other thing that's very interesting, and this completely open source, many people in the community have been flying with actually this framework, is that we made a completely new deep reinforcement learning library. This is completely C++ based, completely optimized for any type of device. It's not dependent on any library. And you can see that, the training time is really, really short, really small. And potentially, you can even train on this kind of microcontroller, if you like, right? Not only deploy, but you train on this kind of device. And this is how it compares to all the other, deep reinforcement learning libraries. So this has been more and more used in robotics because you can deploy it anywhere. My students really did it also on an Apple Watch, basically. So the idea is that you can deploy it anywhere, and it's running all on the chipset. So you don't need to do any additional board or any specific architecture because it's independent. And you can see here that, this framework were able to train on 18 seconds, for example, of flight, and then automatically deploy this controller in the environment, even for tracking trajectories in space, right? So that's the overall idea. Very robust also to environmental disturbances and so on. So what we did in the first phase, we basically streamlined here. This is still in Python, but we hope to bring it to onboard sensors and so on. We streamlined into a neural policy that now it's working directly on the chip. And this has culminated, last week with the release of this video where we use meta imitation learning to basically fly any type of quadruped. These were 8 platforms flying all together with the same policy. The policy was just adapting to the different parameter implicitly of the platform you had. So this is now open source, all type of microcontroller, all types of firmware. So there is not really a difference. And what we have shown is that the students was really excited to show that this is working. So we tried the soft drone as well. So it was adapting surprisingly. And then I think he tried to do some switch the propeller. So same experiments we did, in the first case, and it's still flying quite well. And then he started to do some kind of disturbance where actually this is the coolest one. I'll have to show it back because that's where it shows that's really, providing the robustness to the system when it basically does this. That's basically, going over 90 degrees of disturbance, still recovering very well. So we did kind of different types of experiments. So now in the last part, maybe 15 minutes, then I leave some questions. Sometimes the question is, how do this approach scale to multi-agent systems? So the idea here is that all these representation that we've seen could potentially come together, and if you have communication between the robots, you can potentially share this representation to be robust to adversarial attack. Or you can even improve for example, you want to reduce the uncertainty of one of the robot when another robot has a better view. And this is not only relevant to robotics, it's really relevant to fleet of autonomous driving. That's what the future is going to be. So you're going to have like fleets of autonomous cars in the city. And basically what an autonomous car is perceiving will be shared with another one to improve safety and reliability, right? So the idea is that here we're really interested on how can we collect the fused intermittent distributed environmental data for accurate and resilient context appropriate decision making between the different agents. And we're interested in two main tasks. One is the planning problem, so collective task assignment and execution under limited communication. And the second one is the collaborative perception problem. So here the idea is that you have an high-level perception task. For example, each car or each robot has a given sensor input, which represents a view of the environment. And you want that each robot estimates, I don't know, the semantic segmentation from its own perspective or its own depth estimation. But the difference is that you don't want to do it alone, but you want to leverage the information of your neighbor agents in an implicit way to maybe share the latent representation of latent features across the agent so that this becomes basically, you have a better localization or you have a better depth estimation and so on. Potentially, you can even see through walls. So if you have a black image, maybe two of your neighbors can actually sharing information can give you the view and can still let you solve the task, what you wouldn't be able to solve by yourself, right? So really, the main gaps of this method that have been proposed in the literature is that they struggle to deal with the real world complexity and the challenges available in real world, like, communication constraint. Many of the approach, have optimality only if they are distributed and have optimality only, especially in the planning, or if you have full communications between the agents. In other case, perception is a big problem. So many of the approach are for bird eye view. So you have for autonomous driving, but if you have other types of robot motion, these they've not been designed for that. And so people just try simulations. But the other real problem is that, there is a lack of data. At the end of the day, the only data that's available for this task, and it's becoming now, it's for autonomous driving, and it's mostly LiDAR. So that's the idea. And then, many of the framework, as I was saying, to deploy, they are limited to specific tasks, to control or plan. So the approach that we've taken here is that can we leverage learning in this context first, and where learning is useful and where it is not. So we noticed that, first of all, what we adopt is what we call graph neural network. So imagine that, you have a graph that's representative of your robots here. And you can imagine that each one of these robots, which is the age here, has a neural network inside that's doing the encoding of its own information that's receiving. For example, in this case, you have image as inputs, and each robot is encoding its own information, right? So this information is then shared between the robot you can communicate with, and then finally, each robot output its own, high-level task, which is in this case depth estimation. So we'll see that, where is this useful? So we'll see later that this is really useful to scale in terms of number of robots based on how this neural network works. They work out distributed function approximator, basically. That's what we like. But of course, they lack guarantees and so on. So even if they're trained with reinforcement learning and so on, so some of these approaches right now are just starting to be investigated in distributed settings, how with learning can provide safety, right? But first, let me go to the approach. How do we deploy this? So what we propose here is the general framework. that basically, you can use for perception, for planning, for control, and so on. So you just get as input your data, which may be your state, maybe your images, whatever. Then you do the encoding of your feature, you share with the other robot, each robot aggregates the information that comes, and then you decode for high-level perception tasks, or for collaborative plan, right? And so we have shown that this framework, we're going to release it soon online. So this is, for collaborative perception. And so you can show here that, through collaboration, what's the really benefits is that the multi-robot uncertainty for each agent is way lower compared to the single robot uncertainty, right? Then, we tried this in different settings. Here we want to do a mapping task, so we really reconstruct the three views. And this is, for example, semantic segmentations with multiple, the task force identify chairs in the environment. And the last one is, collaborative planning motion of different agents. Of course, combined to that, what we did here is that, especially for the perception task, there is a lack of data. So all the data that we collected with multiple agents in outdoor environment, we made a data set and we released, to the community. And this is, indoor, outdoor, multimodal, sensor corruptions. There is, a foundation model also that delivers zero-shot semantic and depth annotation. The main difference here is that, this is collected not only with respect to autonomous driving. Why do we need this? You need this because it's collected with heterogeneous agents. So you have aerial and ground, and then each agent has different types of sensor. That's what we're interested in the future. So the ground agent has a LiDAR. The camera is probably an aerial robot for payload reasons. So in the future, we would like to combine not only the distributed aspects, but also the heterogeneous sensing that each robot is providing. But there is even more. Each robot moves differently. So potentially in the future, you can also leverage, how each robot moves to what kind of data I need to share with my neighbors, right? Depending on my type of motion, I prefer to share some data rather than some other. These are some of the views that we provided. And also here we show that in case of, for example, collaborative depth estimation, we tried some cases here in this data set. This has a completely corrupted image, one of the three aerial. So this is what each robot is supposed to reconstruct. So the robot on its own is not able to do anything, but collaborating with the other two agents, it's basically able to reconstruct at least a part of the objects in the environment. Right? At the planning level, what we've been interested in, and this is where, this is, this solution, neural solution, they are intrinsically distributed. So they're very good to scale to multiple agents, but as I mentioned, they don't really provide safety guarantees and so on. So what we did here is that for the planning case, we leave to the graph neural network the ability to plan the motions of the agents, but then for their execution, we use optimal control techniques, like for the case of a single robot with second-order control barrier functions to basically guarantee safety and motion execution of this solution. The nice thing is that this is completely, the network can readapt dynamically with this graph neural network, with who you communicate and so on. Everything is done in a seamless way, because you just aggregate what you have around you and then who you can communicate, and then you try to leverage that as best as you can, right? But then it doesn't matter if you have some imprecision, because who is going to save you is this kind of control. But at least you can scale with respect to the number of agents. And here, in this work, we have also provided some nice, theoretical property in when we can guarantee the safety for all the agents based on whatever the control input is and whatever their velocity is in the environment, right? So that's the idea. And these are some of the tests that were shown in the lab, where recently actually we even made the neural network not only to generate like a single goal, but it's continuously updating the goal that's given to the robot. So I don't decide just one goal on the other side, but actually I'm trying to give some guidance, a path in the environment that the robot has to follow. So this is, for example, for doing formation, and then different types of formation. Then later we show that we can deal also with obstacles. So really reconfigure in the environment and so on. So that's the overall idea. So this is in terms of also collaborative planning. So we have shown this working outdoor in the field where they need to go to different types of locations. So that's the overall idea. So to conclude, a few takeaways, I would say. So the first takeaway is that agile, robust flight emerge when autonomy is adaptive, reactive, and grounded in what the robot can actually observe directly. I think it's very, learning efficient models and representation that basically have some kind of physical knowledge into it, definitely improve safety, adaptability, and scalability. We leverage some learning to reduce the deployment time. That's what we're interested in. And some of these approaches now are becoming mature enough that probably you can start to use them to solve what Ken Goldberg called the data gap in robotics. So you need data to work with end-to-end solutions. So how do you collect data is to leverage the kind of setup you made, and definitely the collaboration enhance resilience to failure and mitigate adversarial attack. Of course, this comes with limitations. So if you think about it, for example, robot autonomy has no long-term memory, local safety guarantees only, no semantic reasoning. It's sharing between the multi-robot. We're assuming to share all the information that we had. You can basically make that information shareable according to the type of task, also to the type of robot motions that you have. If the robot can only move straight or can only move going right, maybe you want also to remove that information because the way it's moving will affect how you will share the information with the other robot. So you can make it dynamic aware, basically. And then we use only a single modality. So we would like to exploit the fact that the ground robot has a LiDAR and the aerial has a camera, and we have also some results on that, but they're not published yet. So what we're gonna work on in the future, we're interested in two main directions to resolve those kind of approaches. The first one is to learn implicit predictive representation directly in the latent space, so avoiding reconstruction altogether. So this is what they call open world models. But the idea here is that, rather than predicting your state, you are predicting future images. So that's what the idea is. And those are conditioned to the action of the robot, and you want to basically minimize what the final view of the robot is going to be, or what your forecast prediction is with what, the final goal image that you have. And so you can basically apply all the techniques that we have seen in model predictive control and so on. But really, in this case, everything is defined in the latent space. So you'll have to deal with some lack of interpretability and so on, and also how you design safety certificates for this kind of model. I think this is a completely new area. And then how you generalize this to multi-agent systems, so to the classical collective intelligence. So is really the idea is that each robot has a sort of neural representation. So the idea is, can I leverage this representation and make decisions based on this representation? Or can I do something I was doing here? I have basically a distributed world model. So at that point, you go toward a distributed world model where you're doing forecasting at the single agent level while you're sharing some common information between the teams, right? And here, you can work with heterogeneous sensing and robots. There is the question of what to share and when to share. And, I talk about distributed foundation models, and there is an opportunity also for real to sim rather than sim to real. So all this data, how does it get back, injected into the current simulator to work to better, refine our test before going to the field. So another thing I want to make, so what we do in the lab is that, we produce lots of these robots, so we don't buy anything. This is another strand, that's coming from the engineering side, actually. So what we do is that we don't buy any commercial product. So everything is made in the lab from scratch. We have designers, people that do this, basically that select the components, and then we build all from scratch. Another couple of topics, I didn't have time to speak about that maybe are interested also for transportation are this concept of, autonomous transportation and human-aware interactions. So this could be useful, in construction. This is what I call the future of construction or warehouse automation, where you really have humans that are closely collaborating with multi-agent systems that are compliant. So here we take into account the fact that the system is hybrid, that you can remove the tension of the cable, and here it's basically just compliant to the user motion. The nice thing here is that when we move, it feels what force the human is applying to the structure, but it has no force sensors. So everything is obtaining directly from the motor speeds of your agents, right? So so it's even cheap to realize something like that. Another area we are very interested is the as I mentioned, I show you the fixed wing here. So we started this new project with soaring. So how do we exploit environmental conditions for improving basically the endurance of this type of platform, like ridge soaring, thermal soaring, or dynamic soaring, even on the ocean. This is just from preliminary work that we built on planning and control of this fixed wing, again, all built in the lab. So and then another topic is thermal geolocalization. So to remove the dependence on GPS of this fixed wing, we're very interested in how to leverage thermal information for mapping your thermal view to satellite view to have still a global localization without GPS. I want to thank all the people in the lab and also all the sponsors, and I'm happy to get any questions.
Wonderful talk. I think we can maybe spend 5 minutes to take questions. Yes.
I started mind blowing. I'm so proud we brought you to Berkeley. And I think you have a lot of connections. I'm going to say in a sentence. We are in city planning and civil engineering.
Yes.
Bring a hammer, we have so many names.
Yes.
I'll let more transportation related questions, but we have many
things to talk about. Great, excellent.
I actually have a question. So in all these like deep reinforcement learning and neural network part of this work, like how sensitive is the training with respect to the architecture of it? Like, do you need a very large neural network to make it function, or a small?
No, I think what is we noticed that all the things that we have seen are working on board. So pretty much the architecture is really like limited number of parameters.
Yeah.
What we noticed that, for example, if you want to do something in reinforcement learning,
Yeah.
you want to save time, maybe imitating an expert. That's what we're doing now, for example, in the multi-agent planning. So there, what we do is that when you want to do task assignment, the optimal solution, the centralized solution is known, and you know which one is the optimal, right? So what we do is that we pre-train all the network with the optimal solution, then we deploy distributed. So that's what we do. But what we're investigating now, can you pre-train and then use reinforcement learning to basically learn new behavior quickly, basically? So that are close to optimal, right? So that's where we are going with that. But then, of course, if you put larger architecture, you may get better performance. But then at some point, you need to trade off the time to deploy and the accuracy. Some of those, big transformer will not even fit on the robot right now.
So for example, like I think people nowadays, like after this GPT, like people are interested in using the GPT, like the large transformer to fine tune for almost like every task that people have previously worked on. So, yeah, I was just.
So that would not, so that in my opinion, I see it as an higher level solution where you basically, you can give some high level commands that then get translated, at a different time scale compared to what the robot needs to make decision. And I think that's now what's feasible and would make things work. But if you tell me, can I use I don't know, VLA or something else to go directly from language to action to motor speed of the platform, I wouldn't trust it. So that's it.
Do they have other, yeah, Scott?
Well, yeah, this was fascinating. So I'm gonna ask one question, which I hope just triggers questions from any students in the room, which is, what are you gonna teach? I'm gonna take your class.
Please, we're going to teach next semester 206 and 106B. That's going to be like more classic stuff. Then I want to start a new class where, I was doing all these things before on estimation, like Kalman filter. So the first part would be that. The second part will put all the neural network to do trajectory or system forecasting in the future. So all these parts that we've seen of embedded predictions or neural network to basically predict, future behavior of the system would be interpreted as the learning-based part of the first one that's more like, traditional, I would say.
Got it.
So I'm moving to start a new robotics class next fall. So that's the idea.
And remind us what EE or EX.
It's X 106 206B.
Yeah, and what the names.
What's it?
Robot manipulation and interactions, which is, has to change, should be advanced robotics, like we're working on that. Yes, please.
Hi, Professor. It's so fascinating. Yeah, I'm Giuseppe. I'm a final year PhD candidate in transportation engineering. And I read a lot about your work because I mostly work on physical machine learning and control. And recently I'm also I read a lot about one slides that you explained that you're not fully trusted about all the learning policies. So you actually use the graph neural network to train the policy and then actually deploy it with optimal control.
Yes.
Control barrier functions. So right now I'm also working on that. I actually did a little bit of drone test in the flight room and I deployed the control barrier function. So I guess two questions. First of all is kind of related to what Professor Wu raised. Why do you specifically choose graph neural network to train the policy? Does any other more simpler, for example, multi-layer perceptron help realize that work, or what's the specific reason you choose?
So the specific reason is just in the communication framework, basically. So they're already structured to deal with different network topologies and so on. This comes from the properties of this type of network, but that doesn't prevent you to basically inject at each robot level. You want to use an MLP, you are totally fine to use an MLP. Where the graph comes in, it's in the way the communication round is done between the agents. So the communication rounds, you can choose multiple rounds of communication, because if you do one round, basically I communicate to my neighbors. But if I do to maybe what I communicated to my neighbors, it's expanding to the next layers of agents and so on. So that's where really the property of the graph is. At the single agent, you just need to encode the information. So however you want to encode, that's totally fine.
I see, got it. And then for the second layer is about the deployment. So what's your opinion about introducing learning into control barrier function and all the safety certificates?
That's excellent. So I think that's a way also to scale that aspects when you have very complex environment, because right now we're dealing with, I know the obstacles and I know the robot, but if you need to deal, for example, in the case of even the first part where I show the control barrier function for multiple points, then we're picking basically the most 10 or 20 that were the closest, right? Because that's what we're interested in. but potentially that behavior could be automated by directly learning the control barrier function and without, giving the robot a priori knowledge, okay, just consider the 10 that are closest. Maybe, the 10 that are closest are good in tight environment, but are not good if you are in a much open space where you probably care more, some objects that are further away, right?
Yeah, but like, I think the reason why we want to use learning just for training policy but deploy with control barrier function is exactly because we are not fully trust about the result of the learning because it's lack of some interpretability.
Yeah, it's like some interpretability. Yes, that I agree.
If we introduce that concept into the safety filter, wouldn't that be?
Yeah, that would lose. That's why, you can also think about more physics informed approach where they mitigate the thing, but at the end of the day, it's a trade-off
I see.
between what you want to obtain in terms of computation or how you want to scale with respect to the environment. Yes.
I see, got it. So in summary, you think that learning is helping us to increase the scalability?
I think that's a big factor that we've seen also in the planning, deploying these things, it's extremely fast. And the other thing is that, it's natural. Once you put the node of the GNN inside, you just communicate with who you have close by, and then it's automatically integrating the information for a level perception task.
I see, got it. Thank you so much.
Welcome.
For the interest of time, maybe we can stop the question Q&A session. But you can reach out to the.
Thank you very much. Yeah, the name is this one. Feel free to reach out. We'll be more than happy to chat or meet.
Okay, thank you.
Thank you very much.